For decades, astronomers pictured supermassive black holes as permanent residents of galactic centers, enormous objects surrounded by stars, gas, and dust, quietly influencing the evolution of everything around them. But the universe may be more dynamic than that simple picture suggests. Astronomers have identified evidence for extremely massive black holes that appear to be displaced from the centers of their galaxies, raising an extraordinary possibility. Under the right conditions, a black hole can be kicked away from the environment where it formed. The mechanism behind this begins with one of the most violent events imaginable, a collision between galaxies. When two galaxies approach each other, their stars rarely collide directly because the distances between individual stars are enormous. Instead, gravity gradually distorts both systems. Spiral arms stretch. Gas clouds interact. Star formation can accelerate. And eventually, the galaxies can merge into a completely different structure. Deep inside many large galaxies are supermassive black holes. When their host galaxies merge, their central black holes can eventually sink toward the new galactic center and form a binary system. The two objects orbit one another while interacting with surrounding matter. Over immense periods of time, their separation can shrink. Eventually, the black holes can merge. At that instant, one of the strangest predictions of Einstein's theory of general relativity becomes important. A merging black hole system can release gravitational waves, ripples in spacetime that carry energy away from the system. If those waves are emitted asymmetrically, conservation of momentum requires the newly formed black hole to recoil in the opposite direction. The result is sometimes called a gravitational wave kick. For sufficiently powerful mergers, the recoil could be enormous. In extreme theoretical cases, the resulting black hole could be displaced dramatically from the center of its galaxy or, under favorable conditions, potentially escape the galaxy altogether. Imagine the scale of that event. An object containing millions or billions of suns could suddenly be set into motion across its host galaxy. It would not be moving like an ordinary star. Its enormous mass would make its journey a profound gravitational disturbance. And that leads to another intriguing possibility. If the displaced black hole travels through a region containing large amounts of gas, its gravitational influence could disturb that material. Gas may become compressed. Shocks can develop. And under certain conditions, compression can contribute to the formation of new stars. Astronomers have investigated observations of unusual structures that appeared to contain young stars or star-forming regions associated with rapidly moving massive objects. But this is where caution matters. A bright trail does not automatically prove that a runaway black hole created it. Scientists must establish the object's velocity, determine the ages of stars along the feature, measure the surrounding gas, and rule out other explanations. That process is essential because astronomy often presents images that look extraordinary while the underlying explanation turns out to be completely natural. Still, the possibility itself is remarkable. For much of modern astronomy, black holes have been associated with galactic centers. Now scientists are exploring whether some of these gravitational giants can become travelers. If a supermassive black hole is displaced, the consequences could extend far beyond the black hole itself. Its former galaxy may lose a central gravitational engine. The distribution of gas could change. Star formation could be altered. And the galaxy's future evolution could follow a different path. The discovery of even one convincing runaway supermassive black hole would therefore be much more than a strange astronomical curiosity. It would demonstrate that galactic centers are not necessarily permanent homes. The universe can move even its most massive objects. And somewhere in the darkness between galaxies, there may be enormous black holes traveling silently through space, remnants of ancient cosmic collisions that happened billions of years ago. The possibility of wandering supermassive black holes reveals something deeper about the universe. Nothing is truly permanent. Galaxies merge. Stars are born and destroyed. Black holes collide. Gas moves between enormous structures. And over billions of years, the architecture of the cosmos is continuously rebuilt. This becomes even more fascinating when astronomers look backward in time. The farther away a galaxy is, the longer its light has traveled to reach us. Extremely distant galaxies therefore provide a glimpse into the young universe. And some observations of the early cosmos have surprised researchers. Astronomers have discovered galaxies that appear remarkably bright, massive, or chemically developed at relatively early cosmic ages. These observations do not automatically mean that modern cosmology has failed. Instead, they may indicate that some processes, such as star formation, gas accumulation, and galaxy growth, can occur more efficiently than earlier models predicted. Imagine the early universe as a vast landscape filled with enormous clouds of primordial gas. Gravity gradually gathers matter. Dark matter halos provide gravitational structures in which ordinary matter can accumulate. Gas falls inward, cools, and eventually forms stars. The first generations of stars then begin transforming their surroundings. They produce heavier elements. They emit powerful radiation. Some eventually explode as supernovae. Those explosions distribute newly created elements into space. Later generations of stars and planets can form from that enriched material. The process becomes a cosmic recycling system. But dark matter remains one of the biggest unknowns in this picture. We cannot directly observe it with ordinary telescopes. Instead, scientists infer its presence from gravity. Galaxies rotate faster than their visible matter alone would allow. Light is bent by invisible mass. Large-scale cosmic structures appear to grow within an underlying gravitational framework. This unseen component appears to account for a large fraction of the matter in the universe. And yet, despite decades of investigation, scientists still do not know exactly what dark matter is made of. That uncertainty matters because dark matter influences how quickly structures can develop. If the early universe assembled galaxies more rapidly than expected, researchers must examine every part of the process. How quickly did dark matter halos grow? How efficiently did gas cool? How rapidly did stars form? How did early black holes gain enormous masses? And how much energy did young galaxies inject back into their surroundings? The answers could help explain why some ancient galaxies appear surprisingly developed. But there is another lesson hidden inside these discoveries. Scientific models are not supposed to remain unchanged forever. A model is a framework built from evidence. When new evidence appears, scientists test whether the framework still works. Sometimes it does. Sometimes a small adjustment is necessary. And occasionally, an observation reveals a gap that points toward entirely new physics. That is how our understanding of the universe has advanced throughout history. The strange behavior of runaway black holes, the rapid development of ancient galaxies, and the mysterious influence of dark matter may seem like separate stories. But together, they reveal a universe that is far more active than a static picture of galaxies floating through empty space. The cosmos is constantly evolving. Matter collapses. Stars ignite. Black holes merge. Galaxies collide. Gravity rearranges enormous structures. And the material produced by one generation of stars becomes the foundation for another. Even the atoms around us are connected to this history. The carbon in our bodies, the oxygen in Earth's atmosphere, and the heavier elements inside planets were produced through ancient cosmic processes. So when astronomers discover something that challenges their expectations, they are not necessarily watching science collapse. They are watching the universe teach them something new. Perhaps there are still classes of black holes we have barely identified. Perhaps galaxy formation can proceed through pathways that current simulations do not fully capture. Perhaps dark matter and gravity still contain fundamental secrets. Or perhaps the existing framework will survive, strengthened by better measurements and more accurate models. We do not know yet. And that uncertainty is exactly what makes the search so important. Because the universe does not exist to confirm our theories. Our theories exist to describe the universe. Every surprising observation gives humanity another opportunity to improve that description. And somewhere in the immense darkness, another galaxy may be colliding, another black hole merger may be occurring, and another generation of stars may be forming from material created billions of years ago. The cosmos is not finished. It is still changing.